Every modern application faces the exact same engineering challenge: how to manage vast arrays of digital information without destroying data integrity as the system scales. The definitive mathematical answer to this exact structural problem is the Relational Database Management System, or simply the RDBMS. Enterprise software, from banking ledgers to global e-commerce backends, relies entirely on this architecture. Systems like MySQL, Microsoft SQL Server, and Oracle are all built on this exact foundation. The term relational defines a specific model where data is organized into formal sets, allowing mathematical logic to govern how information is stored and retrieved. If you store data in a flat file, like a basic spreadsheet, you are creating a static list. Simple spreadsheets simply cannot enforce complex application logic, nor can they handle high-velocity, concurrent data transactions without completely breaking down under the pressure. To see how a true database engine works, we can reverse engineer a standard structural model known as the Northwind database. We will examine this architecture at two distinct levels: the microstructure, which is the geometry of individual tables, and the macrostructure, the dynamic links between them. Mastering an RDBMS requires understanding a specific counterintuitive concept. Physically isolating your data into separate containers is the only way to create systemic unity. We begin with the most fundamental storage object within the database, the table. This animated diagram demonstrates a table acting as a strict container. It is designed to hold a collection of related data entries for a single discrete entity, in this case, customers. Looking at the vertical geometry of this table, we have columns or fields. Columns enforce rigid vertical uniformity. They dictate the exact data type allowed. By isolating the customer ID, customer name, contact name, and city columns, the system guarantees that only text goes into a name field and only integers into an ID field. Intersecting that vertical structure is the horizontal geometry, the row or record. Here, we can isolate row number 1, belonging to Alfred's Futterkiste. A single row represents one complete individual instance of the entity defined by the entire table. Because of this grid design, the strict intersection of a row and a column pinpoints a specific, indisputable data value. Intersecting the Alfred's Futterkiste row with the city column yields the precise entry Berlin. But this microstructure has a critical limitation. A single table is perfectly optimized for one entity type, but it fails when trying to efficiently store transactional events over time. What happens to the geometry of this table when customer number 1 places an order? If we simply appended order dates and shipping details directly to the customer's horizontal row, we would have to duplicate their name, contact, and address every single time they bought something. This redundancy destroys data integrity. A single table is structurally insufficient for a complex application. We must create secondary tables to handle entirely distinct concepts. This requires a completely separate data container built exclusively for transactional events, the orders table. This diagram shows the geometry of the new orders table. We have order ID, customer ID, employee ID, order date, and shipper ID. The most important detail in this new structure is the deliberate presence of the customer ID column inside the orders table. This column does not contain descriptive data. It contains no names or locations. It acts entirely as a structural pointer. If we examine a specific transaction, order 10308, we find a customer ID value of 2. The database search logic takes that value of 2, crosses the architectural void, and scans the original customer's table to find the exact match, customer 2, Ana Trujillo. This specific linkage is the core mechanic that makes the database relational. By operating this way, the system achieves massive efficiency. Ana Trujillo's profile data is stored exactly once in one physical location, but it can be referenced by thousands of separate order records without duplication. In database terminology, the original ID in the customer's table is a primary key. The structural pointer in the orders table is a foreign key. Together, they create a permanent structural bond. Allowing independent data entities to dynamically communicate solves the redundancy problem entirely. The next logical step in the business application is the physical requirement to ship the completed order. Where should the shipping company's contact information be physically stored? We introduce the third and final container required for this transaction, the shippers table. Re-examining order 10308, we locate its shipper ID column, which contains the value 3. The orders table is now acting as a central hub, holding multiple structural pointers simultaneously. We can trace the connection from that order directly down to the shipping company, resolving to federal shipping. Look at the resulting macro structure. A single conceptual event, a user placing an order, is now pulling precise data from 3 physically separate locations. This cascade design protects the application. If you update a shipping company's phone number in the central shippers table, that change is instantly reflected for every related historical and future order. This triangular logic scales infinitely. A production MySQL environment uses this exact mechanic to connect dozens or hundreds of tables. An RDBMS is an actively engineered, highly modular engine where strict compartmentalization generates maximum operational efficiency. We have moved from the microgeometry of a single table's rows and columns to the macrogeometry of a fully linked system. Fading the grid lines exposes the structural links that exist beneath the table headers. The engine treats these connections as logical pathways, navigating between distinct storage points to reconstruct a complete view of a business event in milliseconds. This system of data isolation and dynamic recombination provides the structural foundation for MySQL storage engine and query optimizer. It enforces total data integrity entirely through the strict separation of concerns. To master database architecture, you must look past the superficial rows and columns to see the invisible relational geometry binding the system together.